All right, so for today's activity, we're going to do a lab called Beanium on page 10 in your lab book. So go ahead and turn there real quick. In Beanium, it's a very bizarre lab that teaches a freaking fantastic idea. And what Beanium is going to illustrate is why the numbers on the periodic table are not whole numbers. So if you'll just look real quick at the periodic table, that's the wrong one, I'm sorry. That one, I believe. If you'll look at the periodic table, it'll focus here in a second. You'll notice that these numbers are not whole numbers. Now, when we do ours, they're whole numbers because we are rounding them to make math easier. But you'll notice on the actual periodic table, like mercury here, it is 200.59. If we look at cobalt, I guess that's better in the screen. It's a 58.932. So these values here, these are what we are going to call their average atomic masses for all isotopes. So back to page 10. Let me get this back over here. Beanium is going to help us do that. So what we're going to do is we're going to look at beans today, red, white, and black beans, and you have to be a very good accountant today for this lab to work out well. You'll notice right here, you can't see, but the instructions for this lab will be here in this yellow folder. You'll need to pick those up and then follow them through, and I have those here also. The camera will kind of span over and hopefully focus on those in a second. So it says you're about to undertake an experiment to ascertain the atomic mass of beanium, and it carries on. It says research has verified the existence of 3 isotopes of beanium. Now an isotope, iso in science means same, tope essentially just means thing. So we have the same thing, but it must be different in some way. So to us, an isotope is going to be an atom or 2 atoms that are the same atom, but they have different numbers of neutrons, which messes with their mass. Now in this experiment, we have red, white, and black beans. Those are all beans, but they're different in size, just like isotopes are all the same atom, but they have slightly different masses. All right, now I'm not going to go through these directions really very much. Pick that paper up out of the yellow thing and you'll be ready to go. But if you will come over, I guess I need to pan over, and we'll have the lab set up here pretty easy. So first off, there'll be a can of beans, and you can see that right here. They'll just be set on the table. You need a large Weibo or 2 or 3 of them to do this most effectively. And then you'll take one of these little baby like fluoride cups, and then what you would do with that is you would take at least 3 full scoops of beans and put it in your Weibo. Alright, so as you scoop 3, that fills it up just about all the way full. Your next job is not a very fun job. You need to separate these by color, so all the reds, the whites, and the blacks into different piles. All right, and as you read the instructions, it will tell you what to do, and it will give you the data you need to fill in this instruction table on page 10. So you can see the far left number or column says sample number. We don't need to worry about that the way I'm doing it today. Then the next one just says the bean type. Below that you have the number of beans of each color. So after you separate these out, make sure you count them, and that's where you record that data. Then it says mass of beans. So at that point you would take all of your whites and find the mass of them. Then all your reds separately and all of your blacks separately and find the mass of each one. And then you would find the total. The third column over says the mass of single bean atom. Now, if I throw a white on here and just try to measure that bean's mass, first off, it's almost going to be 0. You won't really get much on there. So what we're going to do to find the mass of a single bean is use math. And the instructions will tell you this, but all you have to do to find the mass of a single bean, like a white bean, is you take the total mass of all of the white beans and you divide it by the total number of white beans. And then that will tell you what you have there. And that will give you the average mass of all the white beans and is much more accurate. Okay, the next thing, the far right column, is the percent abundance of the isotope. And we've found percents a lot. To find the percent abundance, you take the number of, let's say, reds this time, and you divide it by the total number of all of the beans. So when you do that, and then multiply by 100, that will tell you what you have. Now, below that table, it says atomic mass of the bean. And let me span over to the instructions real quick and scan a little bit down. To find the atomic mass of the bean, you have to do, whoop, that was too far. You have to do the things right there. And I'm way far away from this, but we'll see if the laser pointer will get us there. You can't really see the laser pointer. But you see where it says atomic weight. That is what we're talking about right now. It's this equation right here. And I'm so far away it doesn't hold still. But you take the percent of the isotope for each one, and that is the far right column. And then you multiply it by the mass of a single one. That's the column second from the right. And then you do that for each color, and then you add those three answers. You should get an atomic mass of a bean that is roughly like 0.3, 0.2, or something like that. Now, once you have all of that done, then you can answer those questions at the bottom. And please recall that the point of this activity is to understand how we find the mass of those actual averaged all of the isotopes of each atom. I said that kind of a disaster. Let me get back over here and see if I can explain what I'm trying to say. So what we're saying is, like cobalt, when we find all of its isotopes and we multiply it by its abundance and we add those together, we will find the average mass of all of the isotopes, which is a little bit odd, but that's why we don't have whole numbers, because we're finding the average mass of all of the isotopes. Now, looking at cobalt, it's 58.9332. It would make sense to us if we could sort of assume then that the most abundant isotope or form of cobalt is 60. And that's why on your periodic table, cobalt will be listed as 60, because it's the most common of all of the isotopes. All right, go ahead, head to the lab, give this a try. If you need help, ask Heather. Once again, the yellow instructions are here. You need 3 scoops of beans, and then you need to be a very good accountant, and hopefully that goes well.